JITX is a way for hardware engineers to write code to design circuit boards. So your input is like high-level code that reads like engineering requirements, and the output is like a detailed schematic level design that's actually rigorously checked for correctness. So it should be passing the vast majority of your schematic checklist. And then we built a compiler that just turns that high-level input into the output.
Hello, everyone, and welcome to the Altium On Track podcast. I am your host, Zach Peterson, and today I'll be talking with Duncan Haldane, fresh off PCB West. Duncan is founder and CEO of JITX, a EDA company, and they have an integration with Altium Designer, and it's actually a very interesting approach to PCB design. Right now, we're running a promo for Altium Designer for new subscribers. Make sure to check out the show notes, and you'll see a link to access that promo. Duncan, thank you so much for joining us today.
Hi, Zach. Thanks for having me.
Yeah, absolutely. Someone from your company came up and talked to me last year at PCB West, and now it's kind of cool to see you guys actually presenting at PCB West. So it seems to have come a long way. And I actually got back in touch with you because I saw your blog on the JITX website, and announcing that you guys got some new funding and showing some examples of what you could do with your product. And I thought it was all very interesting.
Yeah, well, I'm glad you got back in touch. So we announced our Series A from Sequoia Capital and the general availability of JITX. So now you can go to the website and start using it.
So when you say general availability, is this like an open beta?
Nope, like actual product.
Like actual product? That's awesome.
Yeah,
That's awesome. How does it feel? How does it feel to get to that point?
it feels great. When we started, we ran as a design consultancy to test the design tool, and it was kind of a bit frustrating that the rate of helping people was pretty slow, right? A lot of people need hardware, and the best way to serve them was with a product they can just use. So I'm just really excited to be at this point.
So starting as a design consultancy, that's actually an interesting approach into developing a product, because I know that some of the very large consulting firms have developed their own internal products that they later kind of transformed into a publicly accessible product. Was that your intent all along, or did you come into this as a design consultancy and you're doing all of this, and then you have this kind of eureka moment, like, hey, we have this great tool that we've developed, we should make it available to everybody?
Yeah, so this was the plan all along. So we were testing this tool ourselves until it got good enough for professional engineers to use it. So our customers are professional engineers, and hardware people, we don't have much time to evaluate new tools, and it has to be like pretty good immediately for it to be even considered. So we wanted to make sure ourselves that it was solid before releasing it, make sure it's stable, make sure it works, make sure it delivers value in the right ways.
Sure, sure. So maybe before we talk a little more about the product, maybe you can give the audience a little overview of your background, how you
Okay.
came into doing all this. I find that everybody's path into the electronics world is varied and quite interesting.
Yeah, so my path was through robotics. I guess I started in high school, started like kind of bolting things together, and we went down to like the automotive pick yards and like pulled things out of cars and turned them into robots. And that's when first started doing electronics. But I think it became an everyday thing when I was getting my PhD at Berkeley. I was building robots, and they were weird robots. I built a cardboard robot that was like the fastest legged robot on Earth, and I built a jumping robot that weighs about 100 grams. It's about a stick of butter, and has a 4-foot standing vertical jump. And it can jump
Oh,
again.
wow.
And it can jump off walls. And designing these, they're full custom because they were weird. So new materials, new manufacturing processes, and custom mechanisms, materials, electronics, firmware, whole stack. So that's when I really started doing a lot of hardware.
That's interesting. So, I kind of came into this not knowing that I was going to do, you know, PCBs and manufacturing
Yeah.
and hardware. I actually wanted to teach. So it's always interesting when I meet someone who is saying like, yeah, I was building robots in high school.
Yeah, well, and that was my plan as well. I built these robots, but my job was research scientist. I was just supposed to discover new knowledge. And I was like, well, I can come up with this concept for a new way that robots can jump or a new way they can run. And I can write it down on paper in 5 minutes. And then I spend my days drawing shapes. And because that's what design tools are. Like I drew my shapes on the screen. I drew my shapes for the circuit board. I drew my shapes for the machine shop and then made drawings. And I went to see how well I could make the shapes. And I was just starting from scratch on every robot. And it got to be pretty tough because in robotics, like it's an engineering and a science, right? So you engineer the robot so you can build a scientific platform and then share the result. But if you don't have a lot of hardware talent, then you can't design robots that are that complex, right? And if you do, then you spend all your time designing robots and like less time doing the science. And that was kind of my path to JITX. Like I started building these as scientific instruments, and I was on the research professor track. But then I kind of looked forward as like, if I had students, they'd be spending time like this too, right? So I would much rather make hardware engineering much more reusable, much more like productive, and so you can design these things quickly and focus on the science.
So I maybe that informs the approach to how you got into JITX and then what JITX actually is. Is that a fair statement?
Yeah, no. So JITX is a way for hardware engineers to write code to design circuit boards. So your input is like high level code that reads like engineering requirements, and the output is like a detailed schematic level design that's actually rigorously checked for correctness. So it should be passing the vast majority of your schematic checklist. And then we built a compiler that just turns that high level input into the output. And to be clear, it's not a tool for software engineers to start designing hardware. This is like, if you can, it's for hardware engineers. So if you can write a script, some Python, some MATLAB, a little firmware, that's plenty of coding knowledge to use JITX to create new designs.
I have always been a believer that hardware engineers should know a little bit of coding.
Yeah,
Maybe not polyglot, but at least enough to be a little dangerous in some areas and then at least be able to speak to a firmware engineer that might be on their team.
right.
Is that the kind of level of background that you're thinking of here? Maybe they need to know a little bit of one language and they can just kind of jump in and figure it out.
Exactly. Yeah. So we actually built this language purpose built for hardware engineers. Like the way we think as engineers, as designers, you can just kind of like write that in code, and then it becomes like the source of truth for your design. Because like hardware engineers, we kind of love scripting, right? And like we never see ourselves as software engineers, but scripting something's pretty good, and it's very common to like kind of build cathedrals of like Excel spreadsheets, right? And they like do all your design calculations. Maybe you've got 100 of these things. Maybe it's got 30 tabs and it's managing all your connectivity. And that's like way more complex than a JITX design. So
I
yeah, I
will
think
admit
it's
I have a couple of those spreadsheets.
right. Yeah. So my feeling is like that should be a native part of your design. Like how you actually do design when you read PDFs, when you do calculations in spreadsheets, like that should be a first class object of your design tool.
So maybe for the audience out there who says, "Oh, coding," and I'm coding up a PCB,
Mhm.
is there any way you could maybe make the process for getting from what you type in on the screen to the schematic that you output a little more tangible? What exactly is the code doing without, of course, giving away the secret sauce?
No, but we're pretty transparent.
Okay,
By default, I think a lot of electrical engineers approach this with like, "There's no way this could work," right? So you have to show them everything and let them touch everything. So I'm going to be fully open about this. So the way it works is like, let's pick a project, IoT smart water meter. What's your
hmm,
intent for this? So like at every level of the design, your code represents what you want, and at the top level, that's like very high level indeed. Like I need this transceiver, right? I want to use this battery. I need to make sure that this device lasts for 6 years in France on this battery, right? And
sure.
that's like really high level intent. And then you can kind of feed those parameters down into things that generate circuits, designs the RF side of things, adds a transceiver, adds the microcontroller, right? And then you start getting a little lower level, right? Where you're like, well, I need a microcontroller. give me an STM32 that solves my pin assignment problem, L3 series, in stock. And that's like one line of code.
Okay.
And then from the very same interface, there's always something weird on a design. So you can say, like, I need this exact capacitor wired exactly to this pin. So for all the, like, every design's got something a bit different to it, right? So from the same interface, you can do this like fully detailed specification, like type out a netlist, if that's what you want to do. And then you hit compile, and JITX generates a schematic and a board, or a system of boards for your design.
So it sounds to me like the input when you say requirements, right? I think I can understand that, right? Because it's like, generate open parentheses, requirement ABC, close parentheses. I'm, overgeneralizing here, but you get where I'm going. And then I can imagine a set of stuff that happens underneath, which is probably coded in the back end or it's in a library somewhere. And it's trying to balance those inputs with a library of available data that's related to the components that you selected and trying to pair up and find the best compromise between those components. Is that a fair way to describe it?
Yeah, in general, yeah. So we're well integrated with Altium, so we also work natively with your existing designs and libraries. And then you can kind of start enriching them with your intent of like, this little chunk of my schematic I'd like to make parametric. And so if we pick something like a microcontroller, right? So we have a pin assignment solver, so you can represent all your requirements like, oh, I need a CAN bus and like a quad SPI and like two I2C ports and this collection of GPIOs. Right. So we have an index of like, several thousand microcontrollers and a pin assignment solver. It says like, here are the ones for which there's a valid solution. Okay, so I can choose a part from there, or you can like, here's a list and you can like view it as a user and pick something more detailed, right? And then you have a function that says like, okay, set up bypass for this microcontroller, set up reset, set up clocks, set up the programming interface. And, and then you can drill down even further and say like, okay, in the clocks, what are your timing requirements? Okay, you need to use a crystal resonator. And then at the very lowest level are the checks. And this is where like all that like high level magic just goes away and you're just like implementing your schematic checklist. So this crystal oscillator says like, okay, well, I'm gonna look at the balance caps and their tolerance and the board parasitics, and I'm gonna check that the drive level is correct, that I'm not gonna, the pullability is going to be within spec for my timing requirements. It's like all those detailed checks you do on a crystal resonator, those are automated at the bottom level, which means like that's the only way you can rely on this stack of automation that you build up. Because at the bottom level, it's just like the best, how to check your design automatically.
Okay, so using a catalog of tagged data, it really is trying to fill in the blanks using best practices or using data for intervening or intermediate components that can be easily broken down into a set of concrete instructions. And that's what you guys have done, is the process and the concrete instructions, and I guess the tagging of all of the component data. Is that fair to say?
Yeah, I think the simple way to think about it is like you write a circuit and then you write checks for that circuit and you embed them right inside. So you've got your power regulator and all of the schematic checks you need to run to make sure it's going to work, right? And now you can start building higher level interfaces on top of that. You can send that code to someone else and they can use your power regulator without you having to like sign off on the schematic, basically. So when you have that level of checking and correctness at the bottom level, you get to build higher levels of reuse on top of it.
So you said something interesting here, which is send that power regulator, for example, or that microcontroller circuit, for example, to somebody else. I'm imagining in this case, when you say send that design to somebody, it's literally a code snippet.
Yeah. Yeah. It's a code snippet. And the really nice thing is like it represents your intent. So it's not like, you could send a schematic to someone, or you could like send a schematic diff to someone and like, oh, we like colored the different parts, but like, what is this circuit for and how is it going to operate are not answered when you just share schematics. So yeah, you can actually, I don't think we've innovated on software collaboration tools because they're just already pretty good. But yeah, it's a great way to collaborate, especially on a system.
Sure, sure. I think one of the things that starts to come up for some folks when they hear it's hardware generated by code is that you're maybe trying to remove the engineer from the equation in some way. I don't see it that way. I see that
Yeah,
you,
no
you
way.
disagree as well. I
Yeah,
see it more as transforming the job of an engineer a little bit so that they don't have to manually look through all of the different specs for every component that they need. Instead, there's something that can do that kind of mix and match. And now it becomes the engineer's job to, number one, control this tool. And then number
mhm,
two, be able to have a strategy to efficiently check the output to make sure that what was actually delivered is going to meet probably a whole set of other specifications that are very difficult to define in code. Is that a fair statement?
exactly. Yeah. So JITX is very much a supporting technology. Like, I think every hardware engineer you talk to wants to be designing a bit better. Like, they want more productivity, obviously, but they have a lot of really cool ideas that they never have time to test, or not enough time at the bench to optimize the design, or like explore concepts, or maybe they run out of time and they have to add some extra layers they know they could have saved if they had little slack in the design cycle. So JITX is just supporting. You should have this computational tool handle the low level details, which are still important. Like, you need productivity, you need to have a board that works the first time, but there's so much to add past that no tool is going to automate creativity, but you can automate like a lot of the like really rote stuff.
Yeah, that's what I've always felt as especially as the EDA landscape kind of grows and evolves and embraces some of these more advanced computational techniques, including AI, that it's going to change the role of the designer, like we've mentioned. But I think targeting those really rote types of tasks that no one really wants to do anyways, and they always they outsource half of them anyways. That type of
Yeah.
stuff. I think that's a really good strategy for developing future EDA products. And so what you're doing at the end of this is you're giving someone a schematic and you're giving them a placement or at
Mhm.
least just a set of components, right? And the nets are defined and the connections are defined. And
Yeah.
so
So today it's
then
a
oh sorry, go ahead.
yeah it's a so when we export to Altium, no, so you
Hmm.
import to Altium, start working in JITX, export back to Altium. So we export a schematic component library that's optimized for your specific stack up rules materials, and an initial PCB layout, and you can group it or organize it however you want. But it'll at least show you like, here's a dense non-overlapped packing of all your parts, and this is what it looks like when you're thinking about how big this thing needs to be. And the final thing is the check report. Yeah. So you're going to see like, okay, here's the derating analysis for all your components. Here's your I/O checks. You made sure your power supplies are going to turn on. Made sure there's not too much capacitance. We checked like external connectors for ESD. So that like verification report is the third output.
So there really is a lot of data that you guys have gone through on components to be able to match up to these different requirements because you just brought up, components and ESD, right? I think that's
Yeah,
one of those things where engineers kind of rely on very large font lettering in a data sheet to ensure that they've actually picked the right component that's going to meet a spec like that. Or maybe they're doing aerospace and it has to be rad hard. So they're going to Google and they're saying rad hard, right? Rad hard
yeah,
power regulator, rad hard ADC reference, so on and so forth. And that's how they're trying to find this stuff. And so it kind of relies on the part vendor to make sure that they've SEO'd their inventory well enough to make sure that you can actually find this. It
right.
seems to me like this type of system has an opportunity to put some of those maybe more or I guess less well-known parts in front of an engineer so
Hmm.
that they can better uh, find a compromise between all these different design requirements.
Definitely. Um, Especially like, there's always, even if you're not rad hard, there's a new component you want to try. Like, maybe it's like, oh, is this the power design I use GAN FETs for?
Sure.
Uh, so if you can reduce the cost of that experiment, I think just all hardware gets better, right?
Yeah, that's interesting actually, because you brought up GAN FETs. I think this is a good example of something where someone may not know if that's what they need.
Hmm.
And so if they were to just approach it by diving into data sheets or relying on the experience maybe of some of the people around them or their own experience, they might not even think to try this alternative approach to a design. But your
Yeah,
system is able to say, well, this is a feasible approach given your design requirements that you've defined.
yeah, that's exactly what it's for. And what we're building now is, well, a number of things, but among them is more data, right? So we systematize the data by writing checks. So when you think about how do I know that this resistor is going to work in my design? Well, it turns out if you like write every single check you could care about for this resistor and the application it gets used in, you kind of know how you need to model resistors. And then you can expand that out to other component categories. So that's one thing we're doing is like, these optimizations need to be powered by data. And in this industry, the data is not systematic, right? It's nobody provides good data for an automated tool because there just hasn't been one like this, right?
The data problem is interesting because I think the compiling of data around components to date has focused so much on just like search, finding a component, finding a substitute.
Mm-hmm.
The part vendors, or the distributors, I should say, they have pretty good systems for locating a component, or at least a list of components that you can start to, filter through. But at the end of the day, you're manually left to pinpoint something that's going to work decently well, you think, until you then have no choice but to dive into the data sheet. So I think they're only really indexing like the highest level of data. So like the footprint, the voltage rating, the cost, something like this.
Yeah, it's definitely variable. And I should say, like, we're a Nexar partner. We use Octoparts data in conjunction with other things. But we did have to build a different type of database that's meant for part optimization. Like the
Hmm.
types of queries that you do when you're trying to choose like the best set of components are just different and not provided yet by the existing data tools. But because they're oriented, yeah, around discoverability. I think they monetize through advertising largely, and they'll just say like, "Hey, we found your parts. Like we made your parts more discoverable. Your parts are already great, and we put them in front of someone, and it's worth keep sending us your data, right?"
Right. Well, I think there's value in that. I mean,
Yeah,
I like to know that if the thing that's in my design is out of stock, I can very easily go onto Mauser or DigiKey or onto Octopart or wherever else, and it doesn't take horribly long to find something to replace it with that is in stock. So not
yeah,
to knock the platforms that are doing that, but I think you've hit on something, which is that they haven't gone nearly deep enough to actually be useful in any kind of automated tool. Are you guys really the ones on the forefront of doing that, or are there any other companies who have really tried to go much deeper than just discoverability?
I haven't seen anyone. Not to say that they don't exist, but in terms of like turning engineering requirements into a set of like parts you need to go search for and then searching for them, that's kind of a weird thing to do. I haven't seen anyone else do it
Maybe they're in
because if
stealth mode.
maybe they're in stealth mode. I mean,
Hmm.
PCB was like the fastest growing segment of EDA in the last couple of years,
Mm-hmm.
and so people are paying attention now. Which, thank goodness, when we started, like PCBs really need to be fixed. But yeah, things are improving in some areas really quickly, which is great to see. It's great to see the attention in this space. So yeah, maybe there is a new stealth mode company out there.
Well, if they're out there and they're watching this, hopefully they'll get in contact with you, and maybe you
Yeah,
guys
they
can
usually
work
do.
together.
Yeah,
They usually
uh,
do.
yeah. Startups don't really have competition, right? Yeah.
Sure.
So ours is kind of a greenfield thing, and even if you're like entering into the traditional PCB space, the odds that you encounter another startup and say like, "Oh, this other startup solves our problems" at a given customer is like 0% likely.
Sure. Sure. So, the approach here to generating designs, this is totally unique. And when I first saw it, I realized, there's probably this whole other group of young people
Hmm.
who are interested in technology, but who see hardware as maybe difficult for them to get into for one reason or another. Is one of the goals of JITX to really just expand the potential design audience or the potential group of designers that could then get into this field by just giving them another way to get to a piece of hardware? Is that really the goal here?
I think that comes next. So JetX is for professional electrical engineers right now. Typical user has like at least 5 to 10 years experience, but it makes like what I really wanted from JetX is like expert hardware engineering knowledge should be reusable, right? I think the ideal is like think of all the hardware experts you know, and I'm sure you've had them on this podcast. What if their knowledge could be applied to every single design that goes out the door? Right. I think that's really interesting. And once you start automating that level of design, then you can open up to other people that don't necessarily know that and will trust a piece of software to manage it for them, which I don't think describes professional engineers right now. Like that trust has to be built. But later, yeah, like we have a lot of like we're free for educational programs. Typically master's, PhD student, they've built some hardware already, and they're like, just kind of looking back to my grad school days, they look a lot like that. And then we're also building full automation for boards. So new kinds of routing algorithms, new kinds of placement algorithms, checks for physical geometry, because people entering the field need actually more automation than professionals. So not only like are they a bit less willing to pay for things, but they also need more product. Like they really need an auto router. They need someone to make sure that the power integrity of their board is at least decent. Usually they're not trying to do something too challenging, but I found that the product actually needed to support more automation before you get to like really open it up to people that might not be hardware experts.
Well, I think anybody that knows a bit about how I'm going to just go the AI direction here for a moment, but I think anybody
Mm.
that knows about how those tools work, they might look at this and they say, well, it's just recycling old stuff and it's not really innovating. Is the response to that to say, well, it's helping you eliminate reinventing the wheel, so you can focus on building the new and improved part of this system, and it really allows you to, I think, focus your efforts and build better in the area that really is new and there is no past data on it. Is that a fair way to look at this?
I think that's a good way to approach it. Yeah. So I think
Who wants
it's
to
very much
design the
right
same old
now.
switching regulator 20 times, right? you know
Well, I think the future is optimization. So right now, JITX automates like model-based engineering and worst-case circuit analysis, and that's like really helpful, right?
Oh yeah, definitely.
Uh, but then when you think about AI coming into this, I'm not going to use it for worst-case circuit analysis. AI, think of it as a search tool, right? The analyses you do on circuit boards to make sure they're correct are pretty computationally expensive. So you can use some AI techniques to say, like, what about this design variation? Like, just like test all these different ideas very quickly, have a human driving it to kind of do this what if analysis and search better. Um, Rather than replacing, like, I think model based engineering is model based engineering, and you don't need AI in there doing anything.
The last time I had talked to anyone about bringing AI into this kind of generative design process, it was talked about in the same way I had read about in a paper from, I think, 2007 or 2009. Not the newest paper, but it was on adaptive optimization, and essentially it's the computer learns the best strategy for generating the design. Here it sounds slightly different. It's learning the best strategy for picking from a library of related designs based on certain parameters that are most important, and then spitting those back out to you. Because I mean, random search algorithms or directed search algorithms, you mentioned all of that is computationally expensive. I mean, if AI is computationally expensive, I mean, I could just imagine trying to do random search among a library of a million components. I mean, we'd be sitting here for till the end of our lifetimes waiting for a design to generate.
Yeah. Yeah. I mean, I think you can use AI for search in a number of ways. And it doesn't just have to be from a preset library. You can have AI drive some parameters to create new designs that it thinks are going to be good, right? You have AI kind of estimate how good it expects those to be before you proceed all the way down the realization. But what you see in the chip world is like they're really using AI to optimize chips, and it works. Like they have superhuman performance on specific structures. If you look at the PPA they can achieve. Um, so to bring that to boards, you need what chips kind of already have, which is this like dedicated verification software, right? To actually make sure that whatever the AI dreams up is going to work.
Okay. I like that you brought up the shift over to chips because you're right. They are using it pretty heavily to do this kind of design generation, and I think I think for quite a while the PCB world has maybe lagged a little bit in terms of the design capabilities when you start comparing it to semiconductors, and I guess we could say the same thing with manufacturing, at
Hmm.
least in some parts of the world. But the sophistication in semiconductors, it's just through the roof sometimes when you look at it as an outsider. It really seems daunting. So bringing that kind of generative design capability from chips, or that same idea, into PCBs, what does that look like for the designer in terms of like a day in the life? Are they just now everybody's a systems engineer, or is everybody just doing verification? Because if the computer is generating all the designs, what does that mean for the career of a PCB designer? I mean, so many
Yeah.
designers are set to retire, and we need to get a new qualified workforce in here, at least in the U.S. and probably the rest of North America. So given that that's the case, I think we all need to kind of know what to expect and communicate that to the younger generation if we want to convince that group of folks to actually jump in head first and become pro designers.
Yeah. That's a great question. So on the verification side, there's a reason that we baked verification into the language. It's like the fact that you say like, here's how you choose a crystal oscillator, and here's how you check a crystal oscillator, and it's like the same thing that you put in your design. Because my co-founders had a previous project called Chisel, and this was like a high-level language for designing chips. And they, it was developed at Berkeley along with RISC-V, spun out a company called Sci5, using it 10 times more productive on the design generation side, and then verification becomes like even more the tall pole. So learning from that, you bake verification into the language because computers are actually pretty good at verification. It's just like a lot of details to track, and that's fine. So hopefully we don't no nobody has to be like more of a verification engineer. So my hope is that maybe they're more system designers. They're able to design more complex things, or they're able to optimize more. They're able to just like what we need right now is just raw productivity, right? So that we had to have JITX address the part that's not addressed by any design tool, like when you're Googling or reading spreadsheets, or reading PDFs and then typing into spreadsheets, like all that stuff that passes through the brain, like deserves a tool, right? And then I've been gratified by the response from education, like people in education, like the new people that want to enter the field, but they expect code, right? They expect a bit of automation, right?
I didn't think about it like that, but that's actually a good point, right? Their expectation is that this should be a bit more automated in some way. And it
Yeah.
seems like you're really working to serve that right now on the schematic side. But
Mhm.
I think you had mentioned earlier also a bit more on the physical, the physical layout side, possibly the routing.
Yeah, that's right.
Yeah. Okay. Um, I'm going to get on my high horse for just a moment about automation.
Yeah.
So, and maybe not a high horse, but maybe just kind of ask you to speculate a little bit. So, one of the trends that you see throughout, the history of well, I guess the history of the Western world since the Industrial Revolution is, as new automation comes out, um, it creates a sort of stratification those who know how to take advantage of the automation, I guess, do better than those who maybe don't understand how to take advantage of the automation or just refuse to for whatever reason, pick a
Mm.
reason, but for whatever reason, it doesn't happen. Um, is that something that designers should be worried about, or is this really the type of approach to design that the big boys, the Altiums of the world, are going to have to embrace and integrate in some way in order to, you know, first of all, keep up with their competitors, but also to ensure that they're meeting those expectations of designers who are coming into the field and are, expecting this kind of automation.
All right. Good set of questions. So I don't think any electrical engineers should be worried about losing their jobs. Like, we're in a labor shortage right now. All the companies I talk to can't hire enough electrical engineers and are now reaching for automation because they can't hire enough people. So if that's not job security, I don't know what is. Um, I think you're right that not everybody is going to adopt automation. That's fine. Look back at Synopsys, right? So they did languages for chip design back in the 80s. So VHDL came out first as a simulation language, and then Synopsys was like, you know what? This code you're writing over here, we're going to generate schematics from your code, right? And you're going to say what you want the circuit to do, and we're going to produce an optimal circuit that does it. They had the biggest IPO of all time with, I think, about 5% of the total user base. But that 5% could do massively better, right? That's what made the difference for Synopsys. They just help people optimize more, which I think is like a really worthy goal. So it's not going to be everybody, and that's fine. I think the people that it's not still have a lot of job security. And what was the other aspect of this kind of three-part question?
Um, so are the big boys, the Altiums of the world, going to have to embrace this kind of approach because it gets to a point where everybody else is doing it, and that just becomes the expectation?
Yeah, well, I feel gratified that we've been embraced by Altium, at least. And so we're trying to be good citizens. So, like, we work with Altium data, which is not easy. So being able to consume it and then export it back into Altium is like a major part of our development effort because there's a lot of data to handle correctly.
Mm-hmm.
So yeah, we haven't seen any pushback from the Altium or the big three, or I guess the other big two are Cadence and Mentor, right?
Mm-hmm.
Because our tool doesn't compete with theirs. Right? No
That
one's really done this front end of kind of requirements to schematic. Like, once you're in schematic land and board land, like, these tools are pretty good, right?
mm-hmm.
And there's no reason to like re-implement that. And that goes for the chip side as well.
Sure, sure. So I guess I'm wondering, what's next for the platform beyond physical layout in terms of what it can do and what maybe a developer could step in and do. Could the same approach be used for, let's say, code, like firmware?
Yeah, so we've got some hooks into firmware. So like I said, we had that pin assignment solver and the microcontroller generator that'll actually like generate the firmware setup file, at least for STM32, who made that sort of thing easy. We're also building out our database so you can optimize better. And we are, building hooks into the other CAD tools as well to kind of expand the user base a bit, but really focused on Altium users these days.
So in terms of like the firmware generation, I imagine you're spitting out source files, and they probably have all of the libraries and everything just packaged up in one area, and then you've got functions where users can then enter in their custom application stuff, whatever it is that it needs to do internally. But you've at least generated all the connections that are needed to maybe interface with some peripheral or whatever else it may be.
Yeah, so like for an STM32, when we solve the pin assignment problem and try to do it optimized for routability, uh, we know all of the pin assignments, right?
Sure,
And
sure.
you can also set all of like they basically they expose like a lot, so you can do a lot of automation with it. So they you set these like, what's the state of this pin? Is this pull up enabled? And then we also use that information in electrical checks as well.
Okay.
So yeah, that pin assignment setup goes back to I think CubeMX, and like creates a CubeMX project file, and then your firmware sits where your firmware is, and you can just use this CubeMX tool to generate the connection to your hardware without trying to like retranscribe everything every time there's an iteration.
Sure, sure. Um, yeah, I think for anyone that's had to, jump in and maybe go through open source stuff or try and find libraries for their components, and then all of a sudden they realize, okay, I have to write these drivers for these peripherals. It can get a bit irritating,
Yeah,
having to code everything. One thing that I think that I'm wondering about is, you're looking at one side of this right now, which is the CAD tool user. How much engagement have you gotten from the semiconductor vendors providing resources and data and anything else that you might need in order to build out the tool so that it can produce, I guess you could say, more accurate designs, or designs that can address a broader range of constraints?
yeah, great question. So a good amount of interest. So
Okay.
what they'd like to be able to do is have a parametric reference design, right?
Okay.
So right now they have a static reference design. They have one board, one application, or maybe one board, a bunch of applications, every possible application you could squeeze onto it. Uh, but what if you could just say like, well, for what if I can just generate variations of this circuit for every possible need a customer might have? It's like, okay, now what if I could put those like reference design generators together and have like a system generator? That's actually pretty straightforward. So that's what we'd like to. If you're not partnered with us yet as a semiconductor, please reach out. I think it's a great tool for especially applications designs. Uh, yeah, helps a lot.
Almost like WeBench on steroids.
Yeah, yeah, it's just kind of more generalized version.
Yeah, exactly.
Yeah,
Yeah.
yeah. So like Webbench is pretty good for power, and they're like really smart about how they simulate and check these power designs. But it's hard to do that once you get to like functional requirements of like, okay, I need like a building automation solution, and that draws on
Right.
like 7 reference designs, and how do you actually connect those things together? It becomes really
Yeah.
challenging if you're not using like a tool for it.
Right. Yeah. Yeah. It's that next higher level up in the system and then
Yeah,
connecting all the pieces together. Yeah. I see what you're saying. That would be really cool if, everyone, if all the semiconductor companies just released like the JITX plugin or whatever piece of, software is needed to interface with your tool. And then,
yeah,
okay, I download this. Now I've got access to all the microchip. Download this other piece. I've got access to all of, Silicon Labs or whoever else.
exactly. And then they can just design in their products to literally any board. And because engineers have to do that a lot anyway, especially with a component shortage. You're seeing churn and availabilities, and you have to like swap out major circuits all the time. And also, like
Ugh.
semiconductor companies are doing pretty well. Like the leakage current of modern devices is shockingly low, and they want that designed into legacy boards. But surprise, nobody's got the capacity to do it.
Mm-hmm. Mm-hmm. Yeah, so you could very quickly generate that from an existing design
Yeah,
based on some other functional requirement. So I mean, this is just as much of a design update tool as it is a design generation tool, from scratch.
yeah, exactly. And that's why we're excited to be working closely with companies like Altium, right? So you've got these existing designs, you've got a great tool for like finishing the rest of the design. So if you can kind of attach this computational piece and maybe check your design a bit more or do a bit of component selection optimization and just be like a bit more productive as a parallel path, then yeah, you're in a pretty good spot.
That's excellent. That's great to hear. And I'm really excited to see how all of this is going to turn out, because these new approaches to CAD and these new approaches to building designs, I think are so important, especially like you've said, the younger generation expects a little bit of this already. And so it seems like you're going to be here to give them the tools that they need. So this is really interesting. So thank you so much for joining us today. We're getting a little up there on time, but definitely wanted to make sure that the audience out there gets introduced to JITX, and we're going to have some great resources in the show notes, and we encourage everyone to check out JITX and, of course, connect with Duncan.
Okay. Thanks, Zach. It was great being on.
Yeah, absolutely. Thank you. Thanks again. To everybody out there that's listening and watching on YouTube, we're having an Altium Designer promo going on right now. You can access the link to the promo in the show notes, and we encourage you to sign up for Altium Designer if you haven't already. And last but not least, don't stop learning, stay on track, and we will see you next time.